Good afternoon. We are going to do Unit 10, Day 3, Graphing Logarithms Using Transformations. So a lot of this is going to be review, except for the actual graphing, because we haven't done a huge amount of logs. So let's start really quick with the transformation algorithms. And of course, an algorithm is just a fancy way of saying a method, a way to do it. So we're going to take the transformations that you already know and we're going to relate them to logarithms. Now, first thing you know about transformations is the order. Super important. So the order of transformations actually is the same as it's always been. You do horizontal first. And inside the horizontals, you do stretches and shrinks, reflections, and then horizontal translations. After you're done with horizontal, you do the same things, but in the vertical direction. So vertical, stretch or shrink, reflection, translation. So that order is going to stay true no matter what. What is different with logs is where you find that stuff. So I'm going to go through some of the transformations using logs as an example. Okay, so number one, if you want to reflect across the y-axis, and let's say that your base log is just y equals log x. We're just going to assume base 10 to keep it simple. So that's your base expression. So from that, when you reflect across the y-axis, the x is what gets multiplied by the negative. To reflect across the x-axis, the -1 goes to the front and gets multiplied on the outside of the log. So the x stuff is going to be in the argument of the log. The y stuff is going to be outside of the log or in front of it, just not inside it. Okay, so then number two, let's do stretches and shrinks. So horizontal, we're going to do a horizontal stretch and we're going to do a horizontal shrink. Now, both of these are located in the same place. You're going to have log with a number multiplied by the x in the argument, and that's for both of these. What's different is whether it's a stretch or shrink. For it to be a stretch, the b that you're multiplying the x by has to be a fraction. So b has to be between 1 and 0. For example, 1/2. That would be a stretch by a factor of 2. For a shrink, the b value has to be greater than 1. For example, 3x. And then the factor, by which it is being shrunk or stretched is the reciprocal form of b. And we'll go into a couple examples later. So horizontal, stretch and shrink. Then we go to vertical, stretch and shrink. And for vertical, it's positioned outside the log. So it's some number a times log of x in both cases. To figure out which is which, the nice thing about vertical, what you see is what you get. If a is a fraction, so less than 1 greater than 0, then it's got it backwards. This one should be if a is a fraction, it's going to be a shrink by a factor of a. If a is greater than 1, so let me fix this. Actually, here, I'll just white it out. If a is greater than 1, it's a factor, again, by a. What you see is what you get. So same rules as what we've been doing. Reflect, stretch, and of course translation is the same. For horizontal translation, you have something being added to x or subtracted from x. So x plus a would be a horizontal translation, negative a to the left. Remember, it's always backwards. If it's log of x minus a, it's a horizontal translation of positive a to the right. When it comes to the verticals, again, what you see is what you get. So vertical translation. So you have log x plus a number a, that is a translation, positive a up. Log of x minus a is a translation, negative a down. It's what you see is what you get. We love that about verticals. Okay, so those are your basic rules for transformations. And transformations, why were we interested in transformations? We're interested in transformations because they allow graphing without a calculator or without rounding. And as we all know, our calculators round everything. So if we want to actually graph with exact numbers, we have to use transformations. So nothing is rounded when we get to the points. Okay, so I'm going to flip the page, Roman numeral 2. We're going to do some practice, graphing. Okay, so Roman numeral 2, graphing, practice. All right, and the example we're going to do is f of x equals natural log x minus 2 minus 2. Okay, so first thing you're going to be asked to do is to describe the transformation. So let's do that. Remember, x's come first. So inside we have an x minus 2. It's being added or subtracted, so it is a horizontal translation. Just remember, it's always backwards. This is plus 2 to the right. The second one is a minus 2 on the outside, so it's a vertical translation. And when it's outside, what you see is what you get, minus 2 down. This helps us do the point-to-point transformation. And when they're asking you to graph using transformations, they mean point-to-point. Here's where it's a bit of a twist. In order to apply these transformations to this function, we actually need to get some base points or a starting point, and then we can do the transformations to those points. So your base graph is y equals natural log of x. And of course, natural log is always base e. So we can write it in if we want. So in order to get the starting points, we need to change the base into exponent form. And this is for whatever base we happen to have. So in this case, it would be e to the power of y equals x. That would be the exponent form of the base graph. So we're going to calculate our starting points. And remember, whenever you're doing it with the y as a power, you're going to pick the y's and calculate to get the x's. So you work backwards. So I'm going to use 0, 1, and negative 1, our basic 3 numbers. So if I substitute in a 0 for y, x is e to the 0, and anything to the 0 is a 1. Y equals 1, x is e to the 1, which is 2.7. And y is negative 1, it's e to the negative 1, which is 0.4. Those are 3 values you should be very familiar with. All right, so now we're going to do the first transformation, which is a horizontal translation plus 2 to the right. So That is y equals the natural log of x minus 2. But it's plus 2 to the right, so we're going to take the x's, we're going to add 2 to move them to the right. The y's will not change. So you can see how the description helps you get the math right. So 1 plus 2 is 3, 2.7 plus 2 is 4.7, 0.4 plus 2 is 2.4, and the y's don't change. All right, now we're going to do the second one, which is your vertical translation. So we're up to actually the last transformation for this one. It's a vertical translation 2 down. So the x's are not going to change, but the y's are going to go 2 down. So we're going to subtract 2 for the y's. So 0 minus 2 is negative 2. 1 minus 2 is negative 1. Negative 1 minus 2 is negative 3. And the x's don't change. All right, so this is graphing with transformations. We're doing the transformation to get the points. So on your work, I expect to see the points, the description, and the graph. So let's do the graph. And I'm going to move my x-axis slightly to the left to give me some space. All right, so let's start with your base graph. Let's plot those points. 1, 0, 2.71, so 2.7 up 1, and 0.4 negative 1. Now remember, this is actually a log graph. Because it's a log graph, you're going to have a vertical asymptote at x equals 0. Now again, sometimes this confuses people. We use exponent form just to get the beginning 3 points. Then we go back to log form and actually calculate using transformation. So this is still a log graph. So it has a vertical asymptote, and there is our curve. All right, and that is our base graph. Okay, now we're going to plot the second 3 points. It's supposed to go 2 to the right. Let's see if it does that. 1, 2, 3, 0. 4.7 up 1. And 2.4 down negative 1. So, because we have moved the graph to the right, the asymptote must move with it. How far? 2 units, because we translated 2 to the right. So my new asymptote is here. And its equation is x equals 2. So your points get infinitely close to the asymptote without crossing it, and then they shoot off. All right, so that's our second one. Now our third one is supposed to be a translation 2 down. Now 2 down will not affect this asymptote because the graph just slides down it. Let's plot and see. 1, 2, 3 down 2. 4.7, 1, 2, 3, 4.7 down 1. And 2.4, 1, 2.4 down 1, 2, 3. Again, the asymptote has not moved because we did the translation down, not left and right. So it's going to get infinitely close and then shoot off. And this is our final graph. So again, graphing with transformations means you're applying those transformations to the points and making them happen. Okay, last thing I want to do with you on the notes today, Roman numeral 3, is we're going to take a more complicated problem and we're going to list the transformations. And we're practicing this because when it comes to more complicated equations, oftentimes you have to do more algebra than what you would do normally. So here's our example. F of x equals 5 log of 6 minus 3x quantity plus 4. Now, in order to use our transformations, x has to be alone. The plus or minus needs to be afterwards. So we're looking for something like a number and then x plus or minus another number. That's in the argument of log. We need to have the number out front and x by itself. So to get this ready for transformations, I need to change the order. So negative 3x plus 6. Get the x first. Now I need to get the negative 3 off of the x. So I have to actually factor the negative 3 out of both of those, which gives me x minus 2. So negative 3x plus 6. All right, now this is in a form that we can do something with. So also remember your order. It's always horizontal, stretch, shrink, reflect, translate, and then vertical, stretch, shrink, reflect, translate. That order never changes. Our base graph would be y equals log x. That would be what we start with. Okay, and we fixed the equation we were given so that it is 5 log of negative 3 times x minus 2 plus a 4. Okay, so let's start in the beginning. Stretch or shrink in the horizontal direction. So y equals log of 3x. We multiply by a 3. This is a horizontal shrink by 1/3. Okay, horizontal stretch or shrink. Now reflection. Y equals log of negative 3x. This is a reflect across the y-axis. All right, and then translate. So this is where we're going to get into the one that we transformed. Oops. Excuse me. Hit my camera. Hold on. That's supposed to be negative. There we go. That's better. So x minus 2, remember it's always backwards. So this is a horizontal translation plus 2 to the right. Okay, so we've done our horizontals. Shrink, stretch, reflect, translate. Now we're going to do the verticals. I'm going to draw a line here. Now verticals. So we're going to do these outside numbers. So we start with stretch or shrink. That would be the 5. So 5 log of negative 3x minus 2. The 5 is what you see is what you get. So it's a vertical stretch by a factor of 5. Okay, now reflect. Well, we don't have a negative being multiplied at the front of the log, so there is no reflection across the x-axis. So we're going to skip that. We're going to go instead to vertical translation. We do have a plus 4. So 5 log of negative 3 x minus 2 plus 4 is a vertical translation plus 4 up. And that is our list of transformations. So I wanted you to see this algebra. This algebra is really important, how you have to divide the scalar out of not only the x, but anything that's being added to the x. That's important. The outside isn't so much of a deal because the number will be multiplied by the log and the translation number will be separate. That's not like the horizontal. All right, that is all I have for you today. I hope that was helpful. Have a lovely afternoon.